But I think if you make every possible combination, then you don't need to account for the rows backwards because you already have the same thing in the second order.
Pretty sure. If I just did like random, I did like a really small set of numbers.
Yeah, I did.
4 and 5. Like 5, 3, and 4 are really easy. Like you can see like how they wrap around.
All right, so I'll go ahead and get the lecture started because I know a lot of you are very excited because of the homework assignment that's going to be due on Thursday. Okay, so how many of you actually ended up writing a program to generate the sequences? Okay, and did you guys start to notice anything? I mean, did that help you come up with a strategy to come up with the number? No, it did not.
I haven't got up enough numbers to really know, but also just like the sets that I've done.
I think when n starts to go from 5 and then 6, you will start to actually get some more useful information. Okay. So what I do want to clarify is, what is considered, meeting the requirements. So I want to give you guys a few examples so that you know, what counts and what doesn't count. Okay. So let's take a look at the case when n equals to 5. Okay. So when n equals to 5, r equals to 1 is easy. Okay, because everything has a sequence of 1. So that means the chances of getting r equals to 1 is going to be 100% easy. When r equals 5 is also easy because you're basically looking at the whole thing being a sequence. So you have 1, 2, 3, 4, 5 as one outcome. You have 1, 2, 3, 4, 5 as a separate outcome. Then you rotate, okay? And then you say, okay, what if 1 starts here? So you have 1, 2, 3, 4, 5 as one sequence, and then you flip it the other way, it becomes a different sequence. So this is 1. There are 2 ways to count with 1 being at this position. Okay, when you rotate, there are 2 of these 2. So you basically have 2 times 5 or 10 outcomes that will meet the requirement when r equals 5. Is that making any sense? Okay. Yep.
Wouldn't there technically be only like 2 r equals 5s though? Because there's one at the beginning of the set, which is 1, 2, 3, 4, 5, and then there's one at the end, which is 5, 4, 3, 2, 1, I guess.
But this is a circle. This is a circle, so it doesn't matter how you count it.
Yeah. Oh, okay.
So the number assignment itself does wrap around.
It's kind of like there's no starting point, so you can start wherever.
That is correct. There's no starting point. Yep. Now, the trickier one is when r equals 4. When r equals 4, you have exactly the same 10 cases. Because when you have a sequence of 4, where's the 5th one? You just lock down the 5th one. Yep.
So when you had said that there was no wraparounds,
Yep. It's the number itself that cannot wrap around. Okay. So let's take a look at r equals 2, and we'll figure out what is considered meeting this requirement. Okay. So with r equals 2, you have to be careful because when you have 1, 2, and then you make it out of sequence, so you have a 5 and then a 3 and then a 4 here. Okay. This one actually has 2 sequences of 2 because you have the 1, 2 here. And then you have the 3, 4 here. But it is counted as one single assignment that can be like this. Is that okay? And then you can just kind of imagine, okay, in some way, if you think about this whole thing rotating, then you can potentially be double counting it. Now this one you cannot double count. I'll give you one that can be double counted. Okay, so 1, 2, 3, 4, 5. Okay. So this one, let's see, 1, 2, no, I take it back. The other one that can be double counted. Sorry about that. Okay, so this one can potentially be double counted because when you rotate and you say, okay, this is one configuration where we can have 2 sequences. But when you rotate it, you can rotate this one to here and then the 4, 3 to be here. So there's a potential to double count stuff like that. Is that okay? Yep.
For r equals 2, and consider the first case, 1, 2, 3, 4, 5. So is that part of r equals 2?
This one meets the requirement when r equals 2.
I'm talking about the one below that.
Yeah, they will count as r equals 2 as well.
So how many numbers? So that's 1, 2. How many combinations is that? for r equals 2.
For r equals 2?
Yeah.
I don't know exactly,
No,
but that's,
for that 1, 2, 3, 4, 5, the one on the bottom.
yeah.
Right.
Yeah.
So r equals 2. We have 1 and 2, which will satisfy that. We have 3 and 4, which satisfy that. But we also have 2 and 3. We
Yeah.
also have 4 and 5.
Yeah, but this is still only one assignment. This is still considered one outcome.
It doesn't account for r equals 2.
This is also in the set when r equals 2. Okay, let's look at it from the coding perspective because that might be easier. Okay, so I'll give you the pseudocode to qualify a particular assignment as meeting the requirement. Okay, so we'll talk about the pseudocode. Okay. All right, so here's the pseudocode to figure out. Okay, so given there are n slots, okay, and we need an assignment that has at least a sequence of r numbers. Okay. So I'm just going to give you an algorithm that will determine whether that requirement is met or not. Okay? All right? So it's going to be a double loop because I'm going to go through all the positions within the assignment, and then with each position potentially as a starting point, then I'll be going forward and backward to see if a sequence does exist at that point. Now, technically speaking, you only have to go in one direction, but then you'll be looking for both increasing and decreasing order, because counting it backwards is the same thing as counting it forward, except you're looking for a sequence that is decreasing. Okay, all right. So you initialize a global variable. Okay, requirement met. Okay, so I'll just call that met. Requirement met is initialized to be false. This is going to be my shortcut to get out of the loop. Okay, so once the requirement is met, I want to get out of both loops at the same time. So this is going to be what I need to get it done. The outer loop will go through every single position. So I'm going to assume, okay, so I'm going to say A is an array of n integers with numbers assigned. So that way, we know what A is. A is basically just an array. And then we'll use I as an index, and I starts from 0. So the outer loop is going to go where I goes from 0 to n minus 1, because I want to look at each potential start location and say, okay, if I look at this as a start location, can I find a sequence with that as a start location? So I will say, while I is less than n and not met, requirement not met, basically, do the following. And while, so you may not want to just handwrite everything. You might want to just kind of write down the idea behind this, because the way I code is not linear. So when you try to copy on a piece of paper, it gets pretty difficult because you have to insert and then insert some more, and then insert some more. If you're typing, it's easier because you can just kind of mirror what I type. But if you try to write it down on a piece of paper, it gets a little bit difficult. Okay. So inside the loop here is going to be another loop where I try to control the position starting at I, but this is just the offset, okay, within the sequence. So I'll use another variable j. Okay, j starts from 0 as well. And here's the inner loop, which is while j is less than r, because I just need to look for a sequence of r numbers in sequence. So if I can get out of this loop and actually find a sequence, then I'm all done. Okay? Yep.
Is there a reason why you have a do while for the second one?
Do while as
instead of just a regular while?
Possibly, but let me just finish this algorithm first. Okay, so I will stay in the loop as long as I have not finished the entire sequence. But there's also a chance for me to get out of the loop early. which is when things are not in order, right? Okay. But there are two orders. We can go for the increasing order. We can go for the decreasing order. I'll separate those into two cases. Okay. So within each loop, within this loop, I'm just looking for the increasing order. So with the increasing order, I can get out of the loop if the second condition is not met. Because I only want to stay in the loop as long as everything is still in sequence. In other words, in this case, in an increasing order. So technically speaking, the way we express this is when A bracket I, let's see, I plus J, because that is the starting point, is, okay, let's make that R minus 1, because this is controlling the start position, and I just need to compare to the next item. So R minus 1 is enough to terminate. And I guess I plus 1 is here. There we go. Okay. So what I want to do is to focus on the inner loop and kind of explain, how it works. There are two ways to get out of this loop. The first one is when J is at least R minus 1. Now, if J is at least R minus 1, that means I have just found my sequence. I'm all done. The second reason to get out of this loop is the elements are out of order. In other words, A bracket I plus J is actually greater than A bracket I plus J plus 1, which is the next one. Actually, I take it back because they're supposed to be in sequence, so that means this one has to be exactly this one minus 1. Or if you want to do a plus 1 over here, that's the other way to do it. Because we are looking for a sequence, so this is what we're looking for. Is that okay? But what if I plus J or I plus J plus 1 is wrapping around? Well, we can take care of that using the mod operator. So when you look at I plus J, it is not safe to just use I plus J because that can potentially be out of the bound of the array. So you do the wraparound just by using a mod operator. You mod it with n. And the same thing over here, I plus J plus 1, and just mod it with n2. Am I doing okay so far with this code here? Because the mod n is going to take care of the wrapping around. So it doesn't matter where I start, because if I start with quote unquote the last element in the array, it just wraps around to the first one and then the second one and so on. Yep.
My question is, why do you add 1 to the array of A, I plus J plus 1?
Because I'm looking for numbers that are in sequence.
Oh, I got you.
So I'm looking for 3, 4, 5. So 3 plus 1 is 4, 4 plus 1 is 5.
Right.
But I only need to compare twice to find a sequence of 3 numbers. Because I make one comparison to confirm 3, 4 is together, and then I have a second comparison to confirm 4, 5 is next to each other. If both comparisons has an equality, then I have confirmed a run or a sequence of 3 numbers. So that's why, in this case, J has to be less than R minus 1 because, it is the length of the run or the length of the sequence minus 1. The number of comparisons is 1 fewer than the number of items in the sequence. Is that okay so far? Okay. So when I get out of the loop, okay, I want to know whether the requirement is met or not. Now for those of you who have not taken CISP 300 from me, less than a dash is assignment. Okay, that's the same thing as equal to. So how can I tell once I get out of this loop whether the requirement is met or not? Okay, let's think about this a little bit. If the requirement is not met, this condition is the reason why I'm getting out of the loop. On the other hand, if the requirement is met, I'm getting out of the loop because J does equal to R minus 1, or J is not less than R minus 1. So I'm going to use that to basically say whether the requirement is met or not. So whether the requirement is met or not is just J is greater than or equal to r minus 1. Because if j is greater than or equal to r minus 1, I have just found my sequence. I'm done. But this is only going in one direction. In other words, it's looking for 3, 4, 5. But what about the sequence of 5, 4, 3? This is not going to find it. Okay? So I'm just going to use another loop to do it. Now, it may not be the most efficient way to do it, okay, but it certainly is another way to do it. So I'm just going to do a copy and paste here. It's only if it is not met. Okay, so if the requirement is not met, then I'm going to use a second loop to do it. Okay. And the second one is just reversing the order, which means this one minus 1 is the same as the next one. Yep.
What is the value of r equal to?
Say again?
What is the value of r equal to?
R is the same as the R in the homework assignment,
Okay.
which is the length of a quote-unquote run or the sequence. Is that okay? Yep.
For the reverse, does it matter if we walk forward or backwards? So like, do we have to change the reassignment to j minus equals 1 instead of j plus equals 1?
This will work as well because I changed the comparison itself.
Yeah.
So the way I do it is instead of looking for, okay, so the first one will locate, okay, if you look at a linear array where you have index 0, 1, 2, 3, 4, 5, okay? So the first one will find the sequence of 3, 4, 5 because the one that is earlier has to be one less than the one that is next to it. The second loop will do exactly the opposite. It will find 5, 4, 3 because the index I plus 1 mod n has the element or the value at that point has to be one more than the next one. So it's the same thing as starting with this one, but going with the index going in the opposite direction. So you can do it one way or the other. You can change how you modify the index to go backwards, or you can change the way you compare to look for a sequence that is decreasing. So they should be equivalent. Okay? So I'm not claiming this is the most efficient code, okay? But it should work. But this is just the filter, okay? This is not the generate. It doesn't generate all the possible permutations. But once you have all the permutations, this will filter. This will tell you whether the requirement is met or not. But is this answering the questions about what wraps around and what does not wrap around? Is that okay? All right. Any other questions? Yep.
Question about r.
Okay.
Values of r. So for n equals 7, we look for all sequences starting from r equals 3, then r equals 4, or just n equals r. What's like the definition of sequence that we're looking for? Is it 3 consecutive numbers or
2 to n, right?
2 to n? Or starting from 3 consecutive, 4 consecutive, 5, 6, and until the end?
R is the number of, okay, we are looking for a closed form equation or a formula to come up with the chances of finding a number assignment where there are at least R numbers in a sequence within n slots in a circle.
So r can be 1, r can be 2.
R is a number that is going to go between 1 and n.
So 1 is going to be like all of them.
Yep. Mm-hmm.
There's going to be different probabilities. So you want us to add all those probabilities? Or
No,
separate?
I need a function that will take R, which is constrained by this number, and n. N is just 1, 2, 3, 4, and so on. And I want this to be the probability of having an assignment that will meet the requirement of having a sequence of at least R numbers in a sequence within a circle of n slots. Yep.
R has to be from 2 to n, right?
No, R can be 1. It's just a trivial case, but R can be 1. Okay, if you look at this code here, okay, if you just go look at the code, if R is 1, is the requirement going to be met?
Yeah.
And why is that? Okay, let's think about it. Just look at the code. So if you look at the code here and look at how J is initialized. J is initialized to be 0, okay? And let's think about what happens when R is 1 exactly. So when R is 1 exactly, R is 1, 1 minus 1 is a 0. So the first comparison is going to fail. It's going to give you false, because 0 is not less than 0. So it's going to get out of the loop, right? So once you're out of the loop, you get to the assignment. The right-hand side is a Boolean, is a comparison. J is going to be 0 because we never got a chance to increment J. R is 0. Is 0 greater than or equal to 0? The answer is yes, so the requirement is met.
But practically, what is it?
Practically, it means every single way of assigning numbers within a circle guarantees that you will have at least one sequence of one number. It's basically asking the same question as, is an array of 1 sorted? It's always sorted. It cannot be not sorted. There's no way for it to be out of order. In other words, if you look at a sequence of 5 numbers, this is a run of 1. This is a run of 1 by itself. There are 5 runs of 1s in a circle of 5 numbers. So that means it is a trivial case when R equals to exactly 1. Now when R equals 2, it gets a little bit more interesting, depending on what n is. When R equals to n minus 1, it's not a lot of fun. When R equals to n, it's not a lot of fun. It's in between those cases that make things a little bit interesting. Is that okay?
So,
Yep.
So the probability of like the total one will be the sum of probabilities for R equals 1, 2, 3, 4, and so on until the end.
I just need this function. I want this function.
Yeah, because it's going to be different. For R equals 1, it's going to be always 100%. For R equals n, it's going to be another function, and so on. It's going to be like.
That's a possibility, okay? But you have to generalize it. Okay? Now you do have to remember that 0 factorial is not a special case. This is by definition 1. But 1 factorial, whoops, I got the way around. 1 factorial is 1, and so on. So you want to make it as general as possible so that you don't have as many, you have the least number of special cases. Yep.
So basically, for when R equals 1, it's the sum of all possibilities. It's omega, pretty much.
No, because what this really number is we are looking at the number of outcomes that meet this particular requirement divided by the number of possible outcomes, which is our omega. But in this case, this set here is basically the number of ways to assign numbers in a circle where we can find at least R in a sequence.
Which turns out to be omega. The probability of having R
Yes, when
equals
R equals to 1, that turns out to be the same as omega, correct. Yep.
So is omega meant to be the number of unique outcomes or the number of possible outcomes?
Possible outcomes. Omega always represents the space of all possible outcomes. So in this case, I'll give this one away. Omega is the total number of permutations of assigning n numbers. Because if you look at because they're exactly n slots, whether they're arranged in a circle or not is not even important. When you have n slots and you want to assign n numbers to these slots, the first slot has n choices. The next slot has n minus 1 choices. The next one has n minus 2 choices, all the way down to 1. So this gives you the number of permutations of choosing n items out of n. So that's going to be the cardinality of your omega. The big question is, what is the cardinality of the set of outcomes that you're interested in because we're changing R.
So that means you have to change you have to account for duplicates in the numerator as opposed to the denominator?
Well, the omega never really has duplicates because every element in omega is a different permutation. So there are no duplicates in omega. When I said duplicate, I'm just referring to, it depends on how you come up with your formula. Because, in certain ways of coming up with a formula, you might end up counting the same assignment multiple times. There was another hand back there. Yep.
Well, I was just, I was curious too, because when I was working it out, I treated omega, since it's in a circle and position technically isn't relevant, and there can be the same sequence but rotated or whatever, I had to account for that. Is that how you want us to treat it, or should we not account for the cyclic nature of this?
Okay, let's.
Because if you rotated that, say that 1, 2, 5, 3, 4, one position to the right.
Okay, so
that would be a different permutation, but technically it would be in the same order. You see what I'm saying? So I didn't know whether we needed to take that into
So I'm gonna give you guys another partial solution, and hopefully this will be useful. We already know the answer to this one. What is it?
2 times R.
It's 2n divided by n factorial. Okay. Because this is taking the place of R, is the first thing. So this one is, we need this many items in a sequence out of this many items in a circle. Does that make any sense? Well, let's plug in some numbers and see if it makes any sense. We have a circle of only one item. Actually, that doesn't work out. Start with 2. Well, because it doesn't work out because 2n is 2, 1, 2 times 1 is 2, 2 divided by 1 is 2. You cannot have a probability that is more than 1.
200%.
Yeah, 200% of a chance. That only happens in science fictions that are not really science fictions. Science fiction wannabe, we have a probability of more than 100%. No, that cannot happen. Okay, so F22 is exactly, no, that won't work out either. 3, okay, fine. Okay, so 3 is going to work because 3 factorial is 6. 2 times 3 is also 6. 4 is going to work out. 5 is going to work out. So anything that's greater than or equal to 3 is going to work out. Questions? But does that answer your question? Whether something is double counting or not?
I see the 2 taking account for it now, so I think so. Yeah.
Okay. Because I'm counting these 2 as different outcomes. 1, 2, 3, 4, 5. Having 1 as the top item, but depending on whether you're counting clockwise or counterclockwise, they are counted separately as 2 different outcomes. Because these are 2 different ways of assigning numbers. Even though they are mirror images of each other, they're still considered distinct. Yep.
You could reduce that function into 2 over n minus 1 factorial, which represents it treating the first circle on the whiteboard and the third circle on the whiteboard as being the same variant. I think, would that also be a valid solution, or do you want us to put it over n because n factorials are omega?
Exactly the same.
So it doesn't matter?
Doesn't matter.
Okay.
The only difference between these 2 is when n is a really small number, then n minus 1 being a 0 still has a factorial, n being 0 has a factorial here as well. So this will work, all the way down to when n equals to 0. This will work all the way down to when n is only 1, because it doesn't make sense to have a negative 1 factorial. But when n equals to 0, it doesn't really make sense anymore, because 0 divided by 1 is 0, so there's no chance. But when you have no items, are they in sequence?
Well, yeah.
Well, you can say yes, you can say no. The reason why you can say yes is because there's an absence of something out of order. If nothing is out of order, it is in order. Yep.
It's a very dumb question, but I happened to like trouble visualizing how it wraps around or it doesn't wrap around in a sense, could you write that 1, 2, 3, 4, 5 and then the opposite of 1, 2, 3, 4, 5 as the computer would draw it if it was like just
Okay, the wrapping around has to do with when we look at it this way, there's no such thing as quote unquote wrapping around because it's a circle. But when you run the program, when you write the program, unless you use a circular list to implement this, which is going to be a little bit more than what you need. When you use an array has an end. Okay? So let's say we're dealing with 1, 2, 5, 3, 4. Okay? So when you have 1, 2, 5, 3, 4, okay, and I will use this one as the first one. Okay? So we end up with 2, 5, 3, 4, 1. Okay? But then in this case, well, okay, let's say we're looking for a
Sequence of 2.
Yeah, sequence of 2, but it's going to find it because it's going to find the 3, 4 first. So that's not going to work out for our purposes. But you get the idea. When you are at the end, you have to go back to the beginning and see if that makes a sequence. Which is taken care of in the code by doing a mod n inside the indexing operator. Because I can go all the way up to n minus 1, and j can go all the way up to r minus 2. So the sum of those two numbers can exceed the number of items in the array quite easily. But having a mod n will wrap it around to go back to the beginning and count from the beginning again. So the mod n is actually taking care of the wrapping around part. Okay. Any other questions? Okay, I can give you a few ways of thinking about this that is not going to be helpful. So just to point out. Okay.
I can give you an answer made up for me.
Exactly, but sometimes it's helpful. It's just like in my assembly language programming class, sometimes I would artificially put in an error into the program just to show you, okay, when you see this error, it's because of that reason, okay? So this may be helpful. Okay, so you can think about the 5 slots, okay? If you think about n equals to 5 and r equals to 2, okay? So this is one way people can start thinking about it, but there's a flaw in it, okay? So people can say, okay, I know that we can rotate everything, so I only need to look at it from one single index location. It's perspective, because then I guess I can just multiply everything by n, and I'm done, right? Because I can just rotate it. But the rotating part can create duplicate cases. That is the problem, okay? So let's just think of this as a 1, 2, and then a 5, just to break out the sequence, and then a 3, 4, okay? So that's one way to do it like this. So you think about this and go like, okay, we have at least one sequence of 2, we're done, okay? But hey, there's another sequence of 2 over here as well. So this is actually meeting the requirement of R being 2 for 2 separate reasons, okay? And then you say, okay, if I can do this here, I'll just multiply this one by 5, and that will account for 5 of these possible cases. And then in a separate instance, you say, okay, we have 5, 4, 1, 2, 5, where 3, 4 is in the sequence, it is at the beginning. And you say, oh, we'll multiply this one by 5 because of the rotation thing. These two will overlap. Because when you rotate this one to this position, then it becomes the same thing as this one here. So you're going to end up double counting if that is how you think about the problem. So this way of thinking about the problem will give you an answer that is more like this. Because once you lock down this one, how many choices do I have for the first number when n equals 5?
5.
No. 4. If I'm looking for increasing order, the first number can be 1, 2, 3, or 4. It cannot be 5 because 6 is not available as a choice. So you say, okay, out of the 5 numbers, 4 can be possible as the first choice. But once you lock down the first number, the second one only has one choice because it has to follow the first number. Is that okay? Okay, so now we have taken care of 2 numbers. How many ways can we organize 3 numbers? the 3 remaining numbers. There are 6 ways to do it, right? There are 3 factorial ways to do it. Is that okay? So you will think, okay, so this is one way to do it, and then you say, okay, we'll take this number and then use the times 5 to take care of the rotation. This is where these two will collide. They will basically end up sharing. Some cases will be double counted because of this. Is it making any sense? Because the rotation, this part here, is not taking into account that this 3 factorial may have its own increasing sequence, which eventually will rotate back to the first position. Is that okay or not? Any questions? Yep, go ahead.
So, if we're looking for the sequence, we're only going to, that example you have actually has 2 sequences.
It has 2 sequences of 2.
R is equal to 2.
Yeah.
So are we going to find both, or are we just going to find the first one?
No, it meets the requirement. That's all it needs. It meets the requirement. It goes onto the numerator.
What we're counting is how many seating arrangements we can have that have sequences in them, not how many sequences happen.
Mm-hmm.
So usually there are 2 ways to look at this. You can look at it from the subtractive perspective, which is based on constraints, or you can look at it from the generative perspective and say, how can I generate patterns that can meet this requirement? This is the generative approach, which actually definitely has a flaw of double counting something. So the question is, if you know that you're going to double count something, do you know how many times you're going to double count something? Because if you know how many times you double count something, you can just counter that too. Yep.
Okay, in that formula that you put over there, 2n over n factorial, for n equals 3, for n equals 4 and r equals 4, what's going to be the outcome?
Then it's going to be
8 over 24.
8 over 24.
Which is 1/3.
So a third of a chance.
1/3 of a chance.
30%.
Well, let's check that out. When n equals 4, we can actually quite easily enumerate all the possible cases. Let's just check it out.
Yeah, it's correct.
That's what I got.
Okay, well, it does fit into the pattern that we just looked at earlier. Because when n and r are exactly the same, then there's only one way. If you lock down where the 1 is, there are only 2 ways to do it. Because you're either counting clockwise or you can counting counterclockwise. Then you move the 1 to the next possible position, and now you have 2 ways to do it too. Then you move it again until you go full circle. So that's why it's 2n. And that works as long as n is at least 3, that type of counting works. Yep.
If you put the 2 in the numerator, put on the denominator as a 1/2, it ends up working out all the way to 1.
Say that one more time.
If you took the 2 over the n minus 1 factorial and account for it in the denominator, 1/2 n minus 1 factorial. And, I'm on a different thing than you. I'm sorry.
Okay.
Yeah.
Okay. All right. Any other questions? Okay, so to those people who have not written the program, the code to actually generate the cases and see the things that get through the filter, I strongly recommend doing that because that will start to make you kind of know about the patterns a little bit. And then you can start to think about, okay, so how do we deal with cases like this? Yep.
Can we use the ternary operator in our function definition?
Yes, you can use the ternary operator, or you can just use, like the usual conditional statement, like, when n equals 0, or something like that, and the function has a certain form. It's up to you. Yep.
What's the grading criteria for this?
The grading criteria. Okay, remember, I want you to kind of write down the log too.
Yeah.
So you cannot just give me the final answer. You kind of have to tell me how you arrive to the end, how you arrive at the solution that you have. Just brief explanation, like what you tried out, didn't work, and then eventually how did you discover okay, I can see that I'm double counting certain things, and this is the pattern of double counting, and this is why I'm dividing this by this number to take care of the double counting, and basically little things like that.
I see, but does the result count as part of the grade, or is it just what we write, what we do, or?
It counts for a part of the grade, because if I see just the answer and with no explanation of how to get to the answer, I would definitely take points off. So as you think about this problem, just jot down, in Moodle, just kind of jot down, okay, I'm thinking about this being the solution, and then you say, okay, but it doesn't work because in this case, it doesn't count correctly. Just kind of log all that. Yep.
How much is too much on Moodle? Like, how much would you just be sick of reading at that point?
My mouse can scroll pretty quickly, so it's okay.
Okay.
Yep.
I'll leave you in.
In a way, it is helping you to log your thinking process, just so that when you come up with some examples, it's a place for you to kind of track your ideas. Like, okay, I think I'm going in this direction because I can see some potential solution because of this. So this way, if you need to walk away and do something else, you come back. Okay, you can look at you can log back into Moodle and see where you left off yourself, and say, okay, now I continue to test this and see if it works or not. Yep.
Can I write down notes and just take a picture?
That works too, because I'm pretty sure you can include bitmaps into the HTML document. Movies will be a little bit too much, so don't use your cell phone to shoot a 1 hour movie of you thinking on a piece of paper. That will be too much.
You're not gonna agree.
In that case, put it onto YouTube and give me a link.
Really?
And I want it to be closed captioned. There'll be a lot of Okay, so any other questions? Any other questions about this one? I will probably give you guys, I'll just give you guys an extension to next Tuesday. Okay, so that is not going to be an encouragement for the next homework assignment to have an extension.
Can you do the same thing in 310?
No, 310 is easy. That one is actually
That one's easy?
easy one.
All right.
Yeah.
I haven't looked at it yet.
You
I'm
haven't
busy.
looked at it yet?
No.
Okay, but this is only one piece. So given the time extension, I'm thinking more people should, unless you already have an idea of, okay, I think I know the solution. If you're still thinking about, okay, I'm not really quite sure about the pattern of how to count, and I want to look at examples, you might want to finish this entire program. This is only one piece. This is the filter. This one is going to tell you whether a particular assignment meets the requirement or not. But it doesn't do the generate part. And I think last time we talked about the generate part as a recursive subroutine. Okay, so that's what you guys need to do is to do that part as well. Yep.
So should we also create another filter to make sure that one of the R's that we found is not being duplicated from, so we don't get the same pattern twice?
When you do it brute force, you're not going to worry about it.
Yeah, when you do it with brute force, because you're assuming your generate mechanism is not going to generate the same permutation twice, it is impossible to double count. Yep. Yep.
Over there, you wanted a function which will have R and N as parameters. But then on the other board, you wrote a function which has only N as a parameter. Where's R?
Because the R is the first parameter.
But in the formula, where's R?
The first one. This one has. You mean this one?
One level up.
The one
More up.
this
Yeah,
one?
There's no R. Where's R?
This is R. Because R equals N in these cases. So I'm saying that when R and N are exactly the same, this is the closed form already. That's my little gift to you guys. And also when R is 1, the chances is just exactly 1, so that's the other one.
Great. You gave me the ones I already figured out.
Thanks.
Yeah.
But that's confirmation, that's still good. Any other questions? How many people wrote the generate part of this whole thing?
I hope it.
Okay, you did? Okay. Did you do it recursively?
Yes, it is.
Which programming language did you use?
Visual Studio. But it's
Okay. In C++? And you did it using like 6 levels of loops or something like
A
that?
library function.
A library function.
Did you use algorithm?
Yes.
Yes.
Okay.
That's the
In my
one.
430 class, though, we were actually doing a permutation, like function assignment, though, so it kind of worked together in a way.
Oh, wow. Now, I swear I did not talk to the...
You should share that.
Who's teaching CISP 430?
Well, I take it at CRC
Yeah.
while I'm teaching it.
So there's no chance of there's a collaboration in that
Yeah.
case, so it's purely by chance.
Iraj would.
Iraj here?
Iraj is.
Yeah,
I
Iraj
think he's the
Catalan.
only one.
And then CRC, who's teaching it? Sunny?
Well, yeah.
Sunny Huang, okay. Is it online?
Hybrid.
Hybrid?
One class, but then rest.
Do you like it? Hybrid?
I mean, honestly, I don't even show up to class sometimes because it's like you can do everything in class at home. So. Yeah, no, I'm not kidding. No.
Okay. All right.
That's on the internet.
Okay, so I think this is closed for now, so that you have one more chance to ask questions on Thursday, okay? But I do want you guys to kind of code it first, just so that you can look at all the cases, especially when n equals 5 or n equals 6, you can actually look at the pattern and see if you can figure out a way to go, okay, I can see this, okay, let me see if I can code it or to come up with a formula to account for it. All right. Any other questions? No other questions? So we are ready for more math. You mean this is not math? CISP 440. And I think we are talking about discrete probability distribution. We already talked about Pascal's identity. We are now moving on to the binomial theorem. And I think we started on this one already. Let me just check on it. There we go. All right. I think we started on this one already, just in a different form. So if we look at the equation, which is up here, this is the core part, okay? So this is basically saying that if you have 1 plus x and then the whole thing to the power of n, you can spell it out as an equation where I goes from 0 to n, and the number of items, the number of x to the power of I, is the number of combination of choosing I items out of n. I think we talked about this last time. A little bit? Okay. All right. But this is a theorem, okay? Who knows this is not a definition. In other words, this is not by definition. This is an observation and say that, oh, that seems to make sense, but is it actually true? How do we prove that this is true? So when we prove something like this, we are going to prove it by induction. So I'm going to skip over to this part here. Proof by induction has 2 components. The first component is a base case, where you say, okay, let's lock down a particular case and see if the theorem holds true just for that case. Okay? Because you can see that in the theorem, there's a parameter. A particular number can change. In this case, it has the notation of n. So in other words, what we are going to do is to say, okay, let's see if when n equals to 0, is the theorem true in the case of n being 0? So we will plug in 0 over here. So we are saying 1 plus x to the power of 0. We'll also put a 0 here. So we only have one term in the summation, okay? And see whether it works out when n equals to 0. That one is pretty easy, because when n equals to 0, then we have 1 plus x to the power of 0 being 1, but 1 is also x to the power of 0, which is 1 times x to the power of 0, and that works out. Is that okay? Or not? I think that may, well, let's spell it out and see whether it works out or not. So I'm going to do this part on the whiteboard, because it's a little bit harder to express it on using, well, I can, but it's going to be more difficult to read. So if we go back to the theorem, okay, So we are now claiming 1 plus x to the power of 0 is the same thing as the summation of I going from 0 to 0. And then the inside the term is still the same thing, which is 0, 1, 0, choose 1, and then x to the power of I. There we go. Is that okay? Does that look right to you that this is a special case when n equals to 0, but still using the same theorem? Okay, because everywhere there's n, I changed all of those n to 0. That's all. So let's see if this is true or not. Anything to the power of 0 is just 1. Okay, that one's easy. This is kind of like a loop where the start index or the start number is 0, the end number is 0. So we have exactly one term that we have to deal with. That one single term that we have to deal with is when I equals to 0. When I equals to 0, then we're choosing 0 items out of 0 items times x to the power of 0. So we look at this whole thing here and say, 0 choose 0. Doesn't seem to make any sense. I don't know what that number is supposed to be. Well, let's expand it. Okay? Because in general, what is n choose r? When you expand it into factorial, what is it? It's n factorial divided by r factorial times n minus r, the whole thing factorial, right? So we'll go ahead and expand n choose r on 0 choose 0 using factorial. So in this case, n is 0, so we have 0 factorial as our numerator, and then below here, or as the denominator, r is 0, so we have 0 factorial. 0 minus 0 is also 0, so we have another 0 factorial over here. So this is the coefficient, and then we have x to the power of 0 here. So now we will go ahead and figure out, okay, what is 0 factorial?
1.
It's exactly 1 by definition. So we have 1 as the numerator, we have 1 times 1, which is also 1 as the denominator, which is 1. Anything to the power of 0 is also 1, so we have 1 times 1. 1 equals 1 works out. Now, you may look at this and go, well, that's really trivial. How is this going to help us? Well, this is the base case. This is the anchor of proof by induction. This is a very, very important step, even though it looks trivial, by just plugging in a single number into this whole thing. Okay? So the next step is to prove the step, the induction step. So the induction step is to show that if the theorem holds true for case n minus 1, in other words, when you look at the original theorem, if it works out for n minus 1, we also want to prove that it will also work out for n. Now the important part is the if here, okay? Okay? We are assuming that if it does work out for case n minus 1, if we can prove that it also works for the case n, then we are done. The induction step is done. Okay? So let's see how it looks like in terms of using mathematical symbols. So basically, this is the case n minus 1, because if the theorem works for case n minus 1, then we have this part here. Is that okay? So we are saying that the induction is to prove that this, the left-hand side, this entire thing that I have just highlighted, implies the case n. If this implication holds, if I can prove that this implication is true, then the induction step is done. Once you have the base case and you have the induction step also proven, then you're done. You're done with proof by induction. Are we doing okay so far? So we're trying to prove this implication here to make sure that this implication is true for all possible cases. And the way it works out is, I'm pretty sure there are multiple ways to do this, and I can't. I'm just looking for a way to show the equation itself, but it wants to wrap around. Let me change the code so that it doesn't, try to expand it too much sideways. And this is the proof is as follows. I'm just looking for, case is, here's my horizontal scroll bar. And move it a little bit like this. Okay, then we, just a little bit more to the left. There we go. That's good enough. There we go. So this is the entire proof. So we start off with x plus 1 to the power of n, or 1 plus x to the power of n. I think I changed the ordering inside the addition, but it's okay. The first step is to separate, the one of the components out, and then the other side is x plus 1 to the power of n minus 1. So is the first row okay, which is really just expanding x plus 1 to the power of n into one big chunk and one little chunk. Is that okay? All right. So once we have taken care of that, because we are assuming that the theorem is true for case n minus 1, so we can immediately apply that and say that this is the same as this, because we made the assumption that it is true for case n minus 1 already. Is that okay? And then I changed the order a little bit so that the other x plus 1 is now on the left-hand side and not the right-hand side. But that's just being multiplication being commutative. Yep.
Go back to the first line really quick.
Yeah.
Where did we get the duplicate x plus 1 on the right side? Where does that come from? It's x plus 1 n equals x plus 1 n minus 1, and then x plus 1 once again.
Because the left-hand side is x plus 1 to the power of n minus 1, but the other side of the equality is x plus 1 the whole thing to the power of n. So I'm just separating one of the x plus 1 away from the to the power of notation to break it up into two parts. But the one part that has the power of n minus 1 using the induction step, which is assuming it is already true for case n minus 1, that's how we can get to the second row, is to say that, okay, since we assume it is already true for case n minus 1, then we can break it up already like that. Okay? So going from the second row to the third row, how do we accomplish that? That's a pretty easy one. It's just distributing the addition over the second component. Is that okay? In other words, I take the x out of the x plus 1 here, and then multiply to this entire chunk to come up with this term here. In other words, when you look at this term, it is the same thing as this term with everything multiplied by 1 more x. And that's why we have this plus 1 here. Is that okay? All right, okay. The other one is exactly the same, because this part here is accounting for the 1 multiplied to this summation. And that becomes the second part, or the right-hand side of the overall addition. Is that okay? Are we okay going from the second row to the third row? Okay. From the third row to the fourth row, okay, what is changed? Okay, if you just compare those two, what is being changed? The first one we notice is we kind of changed the indexing a little bit with the one to the left-hand side. You see how this one starts the indexing from 0. This one is starting from 1, right? So how do I take care of that one extra step? Well, the first thing is I change the I plus 1 here to just I, because I have already offset to go from 1 to n instead of 0 to n minus 1. But I also have to take care of the use of I inside the combination. In other words, inside here, this is going from 0 to n minus 1. But if I subtract 1 from the index, then it is also going to go from 0 to I minus 1, to n minus 1, excuse me. Is that okay? So are we doing okay so far going from this summation to this summation? Is that okay? The second half has not changed. Okay, this is strictly just the same as before. Okay, now how do we go from the fourth row to the fifth row? if you're reading this online, you can kind of cheat a little bit and just look on the right-hand side, because the actual reason why we can apply that is on the right-hand side. But without even looking at that, how do we come to the conclusion to go from the 4th row to the 5th row? Well, first of all, what is being changed? From the 4th row to the 5th row. How did I end up with a singleton case of choosing n minus 1 out of n minus 1 times x to the power of n? How did I come up with that one? Where did it come out of?
Isn't that the definition?
The definition of, I look at the case when I equals to n here, the last term of this summation is this term here. Is that okay? So I just take it out of the first summation. And if I take the first case out of the second summation, then I have this guy here. Because the first term of the second summation is when I equals to 0, which means I'm choosing 0 out of n minus 1, 0 out of n minus 1, times x to the power of 0 times x to the power of 0. So basically what I did was to choose the last term out of the first summation, make it its own little term in the addition. I choose the first term out of the second summation and turn it into its own term. And then whatever I have left, I combine that into the middle summation. But that is not possible because by removing the last term out of the first summation, the index is now going from I equals to 1 to n minus 1. By taking the first term out of the second summation, I'm also changing the range of I to go from 1 to n minus 1. So now that in both summations, the index or the loop variable is only going from 1 to n minus 1, I can just take those two, combine them into one single summation, and that's how I went from the 4th to the 5th row. Is that okay? Sort of? Okay. So the trick has to do with summation, where you can just take terms out of it and then change the index or change the range that you're summing over. So what about this one into this one? Going from the 5th row onto the 6th row. What did I change?
We applied our term. If it's valid for n minus 1, it's valid.
Well, okay, so I think you're getting the idea. So we'll do it step by step, looking at each individual term and go like, okay, how did we come up with this? So we'll take a look at the first one here first, okay? Like this one term. What is choosing n minus 1 out of n minus 1? What is that number? It's always 1. Because of this equation here. Is that making any sense? So when r is n, when r and n are exactly the same number, we have n factorial on the top. And then the bottom one, because it has n minus 1 factorial, this becomes just 0 factorial. But r is the same as n, so we have another n factorial here. So n factorial divided by n factorial times 1 is just n factorial, is just 1. So that's why we know that this number here is just 1. Well, if choosing n minus 1 out of n minus 1 is 1, so is choosing n out of n. So that means going from here to here doesn't really do anything. It doesn't change the value because both of those are just 1. Is that okay? And I can do the same thing, well, not quite the same thing here. Well, I guess I can. Okay, I'm doing exactly the same thing here. Choosing 0 items out of n minus 1, how many ways can I arrange that? Can I choose 0 things out of n minus 1? Well, look at the definition. This time we have r itself being 0. Well, if r is 0, then n is the same thing as n minus r, which means we have the same number here. These two cancel out. R is 0, 0 factorial is 1. So now, once again, we have exactly 1. So if this is 1, if there's only one way to choose 0 out of n minus 1, then I can apply the same reasoning and say that there's also just one way to choose 0 items out of n. Is that making any sense? Kind of? Okay. What about the middle part? What about this middle part thing about this whole thing becoming just that? Where have we seen this before? Starts with a P. Pascal's identity, exactly. So this is why the class notes is organized by first introducing Pascal's identity, because we are making use of Pascal's identity in the binomial theorem. Okay, so now that we have all the terms, just fine, just arranged, correctly, how do we go from the second last row to the very last row, where we have one odd item, on its own, a summation, and then another odd item on its own? Well, if you look at this one here, this is almost exactly the same as this, except the range is changed a little bit. Instead of having the summation to go from 1 to n minus 1, I have the summation going from 0 to take care of this item, going to not n minus 1, but n to take care of this item. So I combine everything into one single summation. And why do you think is the one single summation important?
That's what we're trying to prove.
That's exactly it. Okay, that's exactly what we're trying to prove is this expression is the same as this expression, assuming it works for case n minus 1, which is how we got from this expression to this expression. So the first row to the second row makes use of the first part of the implication. The rest are really just algebra and making use of, well, I would sort of call abusing the definition of combination. Because that's basically what it is. Okay, because the trick, if you have to name one trick of this entire proof, it would be this. N choose n is always 1. So if the top number and the bottom number are the same, it's going to be 1. Anything choosing 0 out of anything is also by definition always 1. That is the trick. Okay? The rest is really just counting, pulling things out of a summation, putting things back into a summation, changing the index and stuff like that. And these are the only tricks to this entire proof. That is really specific to what we are talking about, which is combination. Are there any questions about this particular proof? How many people, you don't have to raise your hand, because if you don't want your peers to know that you enjoy doing stuff like this, but you can just kind of track it in your mind. If you enjoy doing this kind of thing, computer science is your field. Okay?
Yes. Said no one ever.
Well, that's telling me that I have that's telling me that I have 10 more minutes to go in this class. But if you enjoy proving, doing proofs like this and going like, oh, this is kind of fun, then computer science is your thing. Okay, you can do programming, but you can also do the math part of computer science. What if you don't enjoy doing this sort of thing? Does that mean that you have no future in computer science? No, that's not the case. I mean, you can program. There are many other branches of computer science that is not as theoretical. So, it's just, one way to differentiate your future career. Okay, computer science versus, software engineering versus, development versus, many other choices. So this can help you understand what you like to do, what you're good at, so they can choose your future career, with more comfort. And can you guys guess whether I like doing it or not?
Nerd.
You like to do it.
Nerd. So if you scroll over a little bit more, okay, just to show you guys where you can find the cheat, the explanations are all here. Although they're not really quote unquote spelled out as much, but it's there. Okay. Are there any questions about this proof? No questions? All good? So if I give you something like this in the final exam,
Sure.
How many people are taking or have taken linear algebra? Okay, so did the exams, especially the final exam, did it involve any type of proofs, or is it more like just invert this matrix or find the eigenvalue?
I'm in it now, but I'm in it right now, so I don't know
Yeah.
about the final, but every test has at least one proof in it.
There's at least one proof?
Yeah.
When I took linear algebra, that's usually a mixture of, okay, here's a matrix, find the inverse of the matrix, and then there's usually like, in my case, it's usually 50-50, like half the questions involve some kind of proof, and then the other half are actually just numerically finding the solution of something. I hate the finding solution of something, because one, back in those days, we cannot use calculators in a class like that. So all the arithmetics have to be done by hand. So if one tiny mistake early on will just screw up the whole thing. So I really do not like calculation type of questions, because I tend to make a lot of little mistakes, adding instead of subtracting, and doing the math wrong. The proof questions are the easier ones to me, because I don't need the precision to do it. I just need to come up with the reasoning to do it. So that's that. Yep.
I was gonna say that at the end of linear algebra, there's like 10 axioms that you need to do for each proof on the final. And
Okay.
there's probably like multiple of them.
All right.
I'm gonna get nauseous if I think about that too much.
Really? Okay, so this is the last slide of this particular chapter. It talks about binomial distribution, which is basically saying, okay, but what if the normal distribution will work well when you have a coin that is 50-50 or not a loaded coin. The question is, what if you have a coin that is loaded, so it has more tendency to have heads or has more tendency to have tails? Then what is the probability in that case of getting a particular combination of heads and tails? So the closed form of that probability is expressed like this. So I'll express the first part first. The k has to do with the number of heads, okay? The n is out of that many different tosses. The lowercase p is indicating the probability of getting a head from each toss. So we have actually 3 parameters, but it is arranged like this. The semicolon is not a typo. That's exactly how they want it to be represented. So k, once again, is the number of heads out of n tosses. And then of each particular toss, there's a lowercase p chance that you end up with a head. Okay, so those are the parameters. The closed form of this equation is this one here. This is the actual probability. So the actual probability is n choose k times p to the power of k, because you have k heads, and then we have p minus 1. I think that should be 1 minus p, so I have to fix that. So it's 1 minus p to the power of n minus k, because that's the probability of ending with a tail. Yep.
So for a normal coin, p would be per toss, right?
With a normal coin, p and 1 minus p will be the same. They will both be halves. So you will be dividing the whole thing by 2 to the power of k. Okay, so before I forget, because I tend to do that sort of thing, let me fix it first. So we are looking for a p minus 1 and change it to 1 minus p. So go do that. We're looking for p minus 1 right there, and change it to a 1 minus p. So you can probably see this is how I actually enter the actual text of the notes for this class. And I used to do this a lot too, so LaTeX is not exactly new to me. Yep, it's all fixed. Excellent. Are there any questions about the probability distribution when the coin is not even? Yep.
How did you come up with it?
How to come up with it?
Yeah.
This is entirely based on what we have already talked about. Okay, so if you think about it, okay, let's say you're looking for 2 heads and 5 tails. Okay, so out of 7 tosses, right? Okay. The first thing you have to come up with is how many different ways can we arrange the positioning of the heads versus the tails. Is that okay? Do you remember how we can represent this? Out of 7 tosses, you can make a set of the number of the ordering or the sequencing of the heads, right? So that means we have one way to do it is 1, 2, 1, 3, 1, 4, and so on. So the question is how many different combinations can we get when we choose 2 out of 7 items? Choosing 2 out of 7. So there's exactly this many combinations of arranging the heads and the tails. Is that okay? But for each particular arrangement, you still end up with 2 heads and 5 tails. The 2 heads has the probability of p to the power of 2 because the 2 tosses are independent. The chances of ending up with the first head is p. The chances of ending with the second head is another p. So that's why the chances of ending up with 2 heads out of 7 tosses is exactly p squared. Is that okay? What about the tails? How many tails are we talking about? We have exactly 5 tails, but the chances of each tail is p is 1 minus p. So that's how we come up with that equation. Is that okay? Yep, question?
Just to clarify, so 7-2 is the n choose k to get all possible outcomes, and then p to the power of 2 is
for each combination, this is the probability of each combination happening. But since we have 7 choose q number of combinations, we need to multiply this because there are that many ways of arranging 2 heads out of 7 tosses. Which is also coincidentally, this is also, if p is 0.5, this is the same thing as having 2 tails and 5 heads, when p is the same. When p is not, when p is 0.5. When p is not exactly 0.5, then you have a different number. Any other questions? Yep.
So, just to be clear, because something is so vague. If p is the probability of having heads, let's stay with heads. So we will do 7 over 2, 2 out of 7 multiplied by p squared, because that's the probability of having head. Why are we multiplying by 1 minus p to the 5? Which is
because that explains the probability of getting the tails.
Well, that's the thing. We're looking for heads. We're not looking for tails.
But if you're not getting heads, you have to be getting tails. You still have to account for the probability of the other 5 tosses that you're not interested in.
But that would be 1 minus what we get with the p squared, right?
No, for each of the toss that ends up with a tail, the probability of that happening is 1 minus p. But there are 5 tails, and that's why we have to multiply that to the power of 5. In other words, what we are doing is, in many ways, we are doing this. We are just calculating what is p. Let's say we're dealing with 2 heads first, okay? So we are calculating head, tail, 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 tail. Should not have picked 7 tosses. Right? This accounts for the exact probability of 2 heads first and then 5 tails. Okay? But wait, there's another way to have two heads and 5 tails. Okay? Which is head, tail, head, tail, 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 one more, tail. Right? So this time I have the first toss being ahead, the third toss being ahead, the rest are tails. But wait, there's another way to do it, which is head, tail, tail, head, tail, tail, oops, tail. And that's it. Yep. Do you see why I come up with 7 choose 2? Because there are 7 choose 2 ways to arrange the p's and the 1 minus p's. But each term, once you use the commutative property of multiplication, they still end up with the same thing, which is this one here. So that's why when you add up all of those terms, you just multiply 7 choose 2 to the other term. Is that helping to explain how we come up with this closed form? Sort of?
And this only works for 50-50 kind of situations?
Right.
This only works for like 2 outcome situations?
Yes, that is correct. It only accounts for the case when you have 2 outcomes. But it is already kind of important because people use these as analysis tools to calculate what are the chances that a bit of 1 can be mistransmitted as a bit of 0, and the probability of a 0 mistransmitted as a 1, because noise is somewhat random. So once you know the chances of something happening, then you can use this type of analysis and say, okay, what are the chances that I'm receiving this particular binary sequence, but it really was intended as something else. So you can actually figure out the probability of that happening. And the reason why just knowing head, tail, 1, 0 is important, is enough, is because we can represent numbers in binary, exactly. So 0s and 1s, so the chances of a 1 being misinterpreted as a 0 is just using this. And that's why binomial distribution is particularly useful because of the binary nature of modern computers. Is that okay? I mean, is everything kind of connected? Okay. All right. So we are running out of time today. We have one more class before this assignment is due. I'm changing the assignment due date right now so that you guys have another 5 days to work on. To some people, 5 more days to procrastinate.
I have 4 other classes. I have 4 other classes.